Hi everyone, today we're covering 5.11, catalysis. So we've discussed before, and this is really the main takeaway that I want you to take from this particular topic, and that catalysts are a material that speeds up reactions without being in the overall balanced chemical equation. They do this by providing an alternative reaction pathway that either will lower the activation energy or increases the number of successful collisions. So you can see here, I have my orangish red line that's uncatalyzed. That requires a lot of energy. But this green one hardly requires any energy at all. And so what a catalyst does is it will allow you to access the green pathway rather than the red pathway. And if you ever see a chemical reaction, like an overall chemical reaction, typically a little thing above the arrow there means that you have a catalyst in the reaction. Now, it isn't always as simple as, for example, I add a catalyst, and if I use this little middle reaction scheme here, that the energy just drops as such. Sometimes a catalyst will do that. But oftentimes what happens a lot more is the following, where rather than having, just one transition state, your catalyst allows you to make several intermediates that all require lower energy than the overall reaction was before. And so you unlock a different pathway entirely, where we'll have intermediate 1 and intermediate 2 on the way to our final product. In this case, this is an example of Homer Simpson getting a pizza. At first, he's hungry. Then your first transition state is, which restaurant do you want to eat at? The second one is, what do we order? The third one is paying the delivery person. And then you get fed, rather than over here, cooking the food yourself. So there are 3 catalysts that AP really wants you to know. The first is homogeneous catalysts. The second are heterogeneous catalysts. And the last ones are enzymes. These are essentially biological catalysts. There would allow all the chemical reactions to happen in our body at any given time. So you might imagine a homogeneous catalyst are where reactants and catalyst are all in the same phase. So this, for example, would be if I had this reaction, CH3COOH aqueous plus CH3CH2OH, also aqueous, reacting under equilibrium with aqueous sulfuric acid, and you make CH3COO CH2CH3, which is also aqueous, and some water, which is liquid. In this case, and actually I apologize, this should be liquid, not aqueous. In this case, you see that the reactants and my catalyst are all aqueous. And so this is an example of a homogeneous catalyst. And so what you do is you just dissolve everything in the same catalyst in the same solvent, and then you run your reaction with that catalyst. Heterogeneous catalysts, as you might imagine, are in a different phase than the reactants. And so this is actually a reaction that I've done quite a bit myself, but let's say we take C2H4 and you react it with hydrogen. You can react this with a catalyst, which we call palladium on carbon, and this will make C2H6. And so palladium on carbon is essentially just a bunch of carbon atoms, like literally graphite powder all packed together. And on top of this carbon, you have a few palladium atoms just kind of sitting in there that's all mixed throughout. And what will happen is what's kind of depicted in this picture. So you can see here, we have hydrogen coming onto the surface, and you have carbon coming onto the surface. It'll split the hydrogens apart, and then it will also kind of hold onto that carbon. And what it does is just holds everything in place so that those hydrogens can easily pop right on and then form your new C2H6, which then desorbs from the metal surface, and then that metal surface is free to continue doing the chemistry over and over and over and over again. Now, the last kind of catalyst that we'll learn about, and this is kind of goes more to biology, but biology and chemistry often overlap, are enzymes. These are biological catalysts, and so these are what we typically find in living organisms. They have a region where your reactants will attach, and so you might imagine, and we'll see this on the next slide, but let's say we have this little groove right here for your enzyme. You have that little space right there. and you have a reactant that is the perfect shape for that space. It'll essentially bind to that, and that'll help the reaction happen. This little space here we call the active site of the reaction, and we often call our reactants substrates when we're thinking of biological processes. And so one model that these go by is known as the lock and key model. And so in an enzyme substrate model, the substrate will fit directly into that active site. And so it's almost like fitting a puzzle piece, right? Your enzyme has this perfectly shaped groove. Your substrate has the same exact perfectly shaped groove. They fit together like puzzle pieces. Some sort of a reaction will happen here, which splits it down the middle, and you have to end up getting your two different products. The important thing here is that they are specific. They only do it for that one substrate. They don't do it for everything. That substrate has to fit perfectly within that little keyhole. And now lastly, we've discussed that one of the things that you need for a successful collision is the correct orientation. And so this lock and key model allows both of the reactants, or one reactant, to be perfectly in orientation, that it's more favorable for a reaction and doesn't require as much energy, right? You need the proper orientation for a reaction to happen, and what these enzymes do is essentially force your molecule to be in that orientation for that reaction to happen. And so what this means is that a reaction intermediate is formed that wasn't in the uncatalyzed pathway. And oftentimes that'll happen where catalysts will form an intermediate that has a lower transition state energy than the uncatalyzed pathway. And so rather than just simply lowering the energy, oftentimes it allows you to make intermediates within that reaction mechanism that you previously didn't have that are much lower energy, and so they're easier to make. We'll discuss this more in class, but for now, that's all. Thanks, guys.